everyone. I'm here today to talk about what genetic bases that could help organisms to adapt to a changing environment. Global temperature has increased rapidly since 1970, making global warming one of our most serious issues. Organisms are shifting their latitude and altitudes as a result of climate change. The horizontal axis represents the expected shift, and the observed shift is in the vertical axis. As temperature increases, organisms shift to a polar or to higher elevations. Organisms that don't move or can adapt to the change tactic may become extinct. And organisms facing a rapidly changing environment can colonize another suitable environment or adapt to the change where they are. In evolutionary genetics, there are two ways for beneficial alleles to help adaptations. Waiting for new mutations or selecting from standing variations. The relative importance of the two is still not well illustrated. And understanding this can help us to infer which kind of organism can survive. So the aim of our study is to understand whether the major genetic source of local adaptation is new mutations or standing variations. And we use altitude to test local adaptation because, firstly, there are sharp differences between low and high altitude environments. For example, the temperature and oxygen content. Secondly, the redistribution of species during their post-glacial extinction provide a good analogy for the effect of climate change today. For example, in Taiwan, pollen and spores data shows that conifer forest is once in 900 meters during last glacial period and moved up to about 2,100 meters now. And this provides us a chance to find genetic evidence of adaptation to global warming. And we use Venus relative parallel as our study species. It has a wide latitudinal distribution on the Asian mainland. And in Taiwan, it ranges from the sea level to about 3,000 meters high. The first objective of our study is to understand the genetic basis of its altitudinal adaptation. We assembled a 1 gigabyte genome from a male parabel and annotated about 40,000 genes. Sample 40 individuals from 2 low, the red spatials, and the 2 high, the yellow spatials. And each of the sides we had 10 individuals. Then we calculated the genome-wide distance between these 4 populations. And the results suggest that the populations first separated east-west, then by high and low altitudes. And this gives us a chance to find genetic evidence of parallel adaptation and to minimize local and stochastic effects in our inference of local adaptation. And then we calculated genetic variance for each population. And we find that high altitude population, the blue bar shows, harbors 9% less variance than low altitude populations. And to detect highly differentiated regions between high and low altitude populations, we use genome scan with 10 kb sliding windows. The horizontal axis represents the chromosome positions, and the vertical axis represents the standardized FST values. And after comparing the 4 populations, we arrive at 107 10 kb regions, which is highly differentiated between both east and west high and low altitude populations, but not in 2 lowland populations. And those 107 candidate regions were referred as candidate regions. Within each candidate region, SNPs with the highest DFST value were defined as causal SNP, like this one. And we found 199 in the east and 187 in the west. And surprisingly, none of the causal SNP were in coding regions. And this may imply that regulatory regions may play an important role in altitudinal adaptation in parabole. And then we calculated the allele frequency for each causal SNPs. The blue bar means the high altitudes, and the orange bar means the low altitude populations. And in east and west, we found that low altitude populations have more fixed SNPs, and high altitude population more polymorphic SNPs. High proportion of fixed SNP could be a consequence of genetic drift, but it is contradicted by our finding that low altitude population has more genetic variance. So our results support stronger selection pressures at low altitude populations. Low altitude environments could have been a refugia during glacial periods. And after the glacial period, population started to disperse. Leading edge population moved to the higher elevation, and the trailing edge population stayed and faced an increase in temperature about 9.6 Celsius. So the trailing edge populations could have experienced stronger selection pressure than the leading edge population. And this is why we saw that loss of fixed SNP in low altitude population. The second objective of our study is to infer the relative role of standing variation and new mutations. And continental islands such as Taiwan can be an ideal system to test these questions. This graph shows the sea level in current dates and during glacial periods. And during the glacial period, there was a bridge between Taiwan and the mainland, and it lost stream flow between Taiwan and mainland populations. And after the glacial period, the sea level rose and limited the stream flow. And this could have occurred just 18,000 years ago. So with such a short time scale, we can infer that variance shared between the island and mainland population are inherited from their common ancestor. And to verify the divergent time between Taiwan and mainland populations, we employ a whole genome approach. And this approach only requires one individual from each population. We sample an individual from Jiangsu with 30-fold coverage. The divergent time was estimated about 45,000 years ago during that glacial period. So the stream flow between Taiwan and mainland populations could have been stopped very recently. And we can infer the standing variations as the shared variance between Taiwan and mainland population. And the other variants could be potentially new mutations. And as the next step, we sampled 40 individuals from mainland and found that 60% of variants were to be standing variation in Taiwan population. And about 90% causal SNPs were standing variations. And the higher proportion of standing variation in causal SNP is significantly higher than in all SNPs. And this implies that standing variation might be a main source of advantageous alleles in altitudinal adaptation in parabole. And our study indicates that regulatory standing variation may play an important role, maybe an important source for parabole to adapt to a new environment during the post-glacial expansion. And it implies that when facing anthropogenic global warming, organisms with low standing variations could have been doomed in the near future and need more conservation efforts. And this study need to thank lots of people for helping me collect the samples from Taiwan and China and doing bioinformatics in our collaborators in different institutes and the financial support for the Ministry of Science and Technology. And I also have a poster in the poster section too. And if you have any comments, it's welcome to come. And thank you for your attention.
Anyone have some questions? Still plenty of time.